So guided beams are the most used spring structure that is found in surface micromachine devices. So I am going to draw a diagram here of a very simplified microstructure. So here we're going to have an anchor point. Then we have our spring. All right, so this is my terrible top view drawing of a structure, and I'm going to identify a few things before we talk about what the side view is going to look like. So all of these black rectangles that I've drawn are anchor points. So I'm going to put a little bit of dashes right here. They are where our boundary conditions happen. So all of these are fixed boundary conditions. And then here, where our beam connects to our plate, we have, let's do it here. These are all the blue dashes are the same things. We have guided boundary conditions. So in this particular structure, we are going to have 4 guided beam springs having a length of L, a width of W, and when I draw the side view, we'll define the thickness T. And we have a force. Actually, the force is going to be acting into the page on the plate, which is going to cause the beams to deflect downward. Okay. So from a side view perspective, we are going to see something like this, and this will be a very exaggerated representation. So that bit right there is just representing one of our anchors. This is also one of our anchors. And then I'm going to try to draw this as best I can. Something like this. So we have almost an S-shaped deflection, like so. And then here is our plate. And in this particular case, I'm just making my plate very thick so that you understand that the plate is effectively incapable of bending. Okay. So once again, we have our fixed, whatchamacallit, boundary condition, our guided boundary condition here. This is the thickness of our spring, and then our force F is acting on the top surface of the plate in order to cause a beam deflection downward. Okay. So as I said a couple of moments ago, each of the beams which connect the central plate to the outside anchor points is considered a guided beam spring, okay? The most simplified approach to analyzing a structure like this is to consider each guided beam spring as two cantilevers with a length of L/2 in series. So I'm going to put something here. Effectively, we have one beam that's experiencing cantilever deflection down, this guy right here, and then this cantilever is experiencing deflection up, and we're going to treat it as two cantilevers in series with some total amount of displacement. Because we're going to treat this system as two cantilevers in series, we first need to very briefly review what the rules are for combining springs, okay? So as a brief guide here, let's talk about Hooke's law for parallel and serial springs, okay? So hopefully we all recall from our freshman physics classes that Hooke's law, which we've actually used in this class, F is equal to Kx. So if we apply a force on a spring with spring constant K, it deflects by some amount X, or extends, or however you want to quantify that spring displacement X, okay? So if we have two springs connected in parallel, let me draw a little picture representing something like that. So let's say that this is a spring having a spring constant of K1. This is a spring having a spring constant of K2. They are connected in parallel. And we're going to anchor this bottom plate and apply some force F in this direction. Both springs have to stretch by the same amount X, okay? So the total force, F total, acting on the system will be given by the force experienced by spring 1 plus the force experienced by spring 2. Using Hooke's law, we can write this as K1x plus K2x, or K1 plus K2 quantity multiplied by X, which could be written as the equivalent spring constant KEQ times the common spring deflection or spring displacement X, which in turn tells us then that our equivalent spring constant is simply K1 plus K2. So springs in parallel add like resistors in series, okay? If instead we have a series connection, so let's say that we have a plate that we're pulling up with some force X. Here is a spring with a spring constant K1 connected in series to a spring with spring constant K2. And then we anchor this bottom node. What we're going to find is that instead of the forces adding together, the displacements add together. So the total displacement experienced by the combination is going to be the displacement experienced by spring 1 plus the displacement experienced by spring 2. Since they experience the same amount of force, we're going to have F over K1 plus F over K2 looks like F times 1 over K1 plus 1 over K2, or F divided by some equivalent spring constant, where we can see that our equivalent spring constant, KEQ, is equal to go away thing. Sorry, trying to make this, there we go. One over K1 plus 1 over K2, and then we take the reciprocal of the combination. So springs in series combine like resistors in parallel. Okay, or we could say that springs combine like capacitors do would be another way to do it. All right, so using this information and what we derived for cantilevers on Monday, because today is Wednesday, right? Yeah. The spring constant for a guided beam spring, sorry, scrolling so much here. We will find that our spring constant, let's call it KGB, will be twice divided by 3. Actually, let's do this slightly differently so you'll know where these things are coming from. Sorry. 2 over the spring constant of a cantilever beam, right? Because there are 2 of them in series, and because they're going to have equal lengths, the cantilever portion will have equal spring constants to the -1 power. So that's going to look like two divided by 3EI divided by the quantity L over 2 cubed. All of this raised to the -1 power. We're taking the reciprocal of it. So doing a little bit of math here. The L on the very bottom, when we cube it, is going to wind up giving us an L cubed in the numerator. So that's going to be 2 L cubed. The 2 cubed in the denominator of the denominator, or actually the 1 over 2 cubed in the denominator of the denominator is going to give us a factor of 8. 8 times 3 is 24. So we have 24 EI here, all of this to the -1 power. 24 over 2 is 12. So 12 EI over L cubed, where L is the total length of the beam. So this is our spring constant of our guided beam structure. Using Hooke's law, we can see that our displacement, Z, no problem. If I need to slow down, please tell me to do so. I do not mind at all. Also, at some point, I will get off my lazy ass and upload all of these videos to YouTube and Moodle as well. Hopefully soon we shall see what happens. But if I'm going too fast, please stop. Okay. All right, so using Hooke's law, the displacement that we are going to see, and I'm calling it Z because we are doing a downward displacement, is going to be FL cubed over 12 EI. Okay. Our maximum amount of stress and all that kind of stuff should be effectively the exact same thing we saw with our cantilevers, because we're considering the system to be 2 cantilever beams in series. Okay. All right, now our last spring. Torsional springs. All right, so the springs that we've dealt with to this point give us linear displacements. A torsional spring is designed specifically to give us some sort of angular displacement. So if we think about how the TI digital micro mirror devices work that we talked about on our, I guess it was the second day of class, might have been the first day of class, we saw deflection of plus or minus 12 degrees depending on how the array was actuated. That has to be carried out by a torsional spring because we want rotation of the microstructure, not deflection of the microstructure, okay? So let's consider a beam with a rectangular cross-section because that's the type of beams that we're going to deal with that is experiencing a torsional moment. So I'm going to call this dimension A. Our beam will have some length L. Like so. This dimension will be B. There is a angular deflection that we're going to call theta when this beam experiences a torsional moment or torque M of T, okay? I'm not going to derive really any of this stuff, honestly, because I didn't have a statics textbooks on me, and I watched Dr. Schwanbaum's videos and he just used the damn table. And so what's the point? So the angular displacement theta is given by the torsional moment M sub T multiplied by the length of the beam divided by J times G, where MT is torsional moment. Measured in Newton meters. L is our beam length. J is our rotational moment of inertia, measured in meters to the fourth power. And G is our shearing modulus of elasticity. For a beam with a rectangular cross-section, our rotational moment of inertia, J, will be AB cubed times 1/3 minus 0.21 B over A multiplied by 1 minus B to the fourth power over 12 A to the fourth power for B is less than or equal to A. Okay. So what we're going to do here, this is literally an equation just from a textbook. Actually, it's a combination of equations from two textbooks that I made work to suit my needs, but that's neither here nor there. Because this is a spring, we're going to effectively force Hooke's law to work for this. So what I mean by that is Hooke's law for torsion, MT, will be given as K theta. So this is going to be our rotational spring constant multiplied by theta, which is our angular displacement. So if we rearrange this expression, we would have theta is equal to our torsional moment divided by our spring constant. And since our angular displacement is also equal to MTL over JG, we can see, actually, let me do it below here, that our torsional spring constant, K theta, is just JG over our beam length, or G times AB cubed over L, 1/3 minus 0.21 B over A times 1 minus B to the 4th power, 12 A to the 4th, like so, where our rotational spring constant is measured in Newton meters, which is different than our linear spring constants, which are in newtons per meter. So for a torsional moment, M of T, caused by a force F applied a distance capital L away from the beam, our angular displacement theta will be FL divided by our spring constant. And then if we wanted to know, well, it would require me to work a numerical example, which I don't think we have time to do. So we might revisit this, or I might work out an example and then just upload that so that you guys can look at it to see what the displacement of the structure that we are applying the torque to would look like. But the angular displacement is good enough. If we know that and we know how far away we applied our force, it's just that angle times that capital L gives us the displacement of the thing we applied the force to. So anywho, all right, so this is all of our springs. So we are roughly 2/3 of the way done with our review of things. Now let's get into electrical things with a extraordinarily truncated review of semiconductor physics. All right, so the basics, right? Semiconductors are a group of materials whose electrical conductivity sigma, and I'm going to put sigma E here, lies between that of conductors like copper and silver, and insulators like glass and silicon dioxide. There are two fundamental types of semiconductors. So we have elemental, semiconductors that are made up of a single element. So this might be carbon in the form of graphene or carbon nanotubes, silicon, and maybe germanium. And then we have compound semiconductors. And there are a ton of different compound semiconductors. Effectively, a compound semiconductor is just one that's made of more than one element. So you could have group 4. So silicon carbide, SiC. So this is a compound semiconductor made out of 2 materials that could be elemental semiconductors, or silicon germanium would also work. Then we have group 3-5 semiconductors like gallium nitride, or as the folks at the Air Force, when I worked there, like to call it GaN. Indium antimonide. So this is INSB. There are others. And then we could have group 2-6. So this would be like zinc selenide, or cadmium sulfide, CBS. And there are others, and we could go on and on. There are some semiconductors that contain 3 materials, 4 materials. We have all kinds of weird, almost like ceramic semiconductor materials where the ratios of the different compounds are played with to get different characteristics. We could talk about just compound semiconductors for 3 damn days, and we wouldn't cover literally all of them, their uses and applications. So we're going to stop here because you get the gist of it. Elemental semiconductors contain a single element, compound semiconductors contain multiple elements, and the combination of the elements has some influence on the behavior of the semiconductor, both electrically and mechanically. All right. Okay, so let's circle back out here. But not all semiconductor materials are crystalline in structure. And so we'll have some that are face-centered cubic, some body-centered cubic, some diamond crystal lattice structures, all of that kind of good stuff. If we look particularly at silicon, because that's our most common thing, the silicon crystal structure is a diamond or zinc blende crystal lattice, which means there are 2 face-centered cubic crystal lattice structures interposed with each other, where each silicon atom is covalently bonded to 4 neighbors. So in a 2D plane, that would look something like this. Let's put this here, this here, this here, this here. We're just going to look at a portion of this to talk about a couple of things. So this is the nucleus of the atom, effectively. I'm going to give the nucleus a charge of +4. We'll talk about why in a moment. Each of these silicon atoms has 4 electrons in its valence band. So what that means is that covalent bonds are going to form between each silicon atom. So they're effectively sharing an electron to fill up their structure. Like so, where this bit right here represents a covalent bond, where an electron is shared between 2 neighboring silicon atoms, and this bit right here is a silicon nucleus. Okay. So can I actually, let me scroll back here. Can I go on to the next page, or you guys? Okay. So let me do capital T for temperature. Are we okay with me using capital T for temperature right here when we're not talking about any kind of stresses? Okay. So at T, specifically at 0 K, so that we know we're dealing with a temperature. Silicon has an energy band structure that looks like this. So this is electron energy measured in electron volts. This is going to be a bit exaggerated, but that'll be okay. So we have 0 electron volts down here. This energy level is the energy level of the valence band. Our valence band will be full of electrons at T is equal to 0 degrees Kelvin. This is the energy level associated with the conduction band. And then this is the energy level of the conduction band plus chi, which is the electron affinity, I believe. So this is our conduction band, and it is completely empty. Of electrons, okay? So at this temperature, absolute 0, silicon behaves as an insulator because there are no electrons available for conduction. The conduction band is entirely empty, okay? Just as another quick thing here, the distance between the energy level associated with the conduction band and the energy level associated with the valence band, this difference is called the band gap, EG, And for silicon, it is 1.12 electron volts. So for temperatures above 0 Kelvin, we are going to have some amount of thermal energy in our system, and that thermal energy is going to cause lattice vibrations. So instead of a very neatly ordered crystal, we are going to see that some of the nuclei are very slightly displaced. So as an exaggerated representation, we might have something that looks like this. So here we have covalent bonds. Right? And sometimes, kind of like a spring, a bond might get stretched a little bit too far. So there's enough thermal energy imparted on an electron to push it from the valence band up into the conduction band. And when that happens, free charge carriers, called an electron hole pair, are generated. So on our energy band diagram, that's going to look something like this. How tall did I make that? Let's see a bit. So here's EV. Here's EC. And we'll see that a hole is left behind in the valence band, and an electron is energized up into the conduction band, and then it will move around through different energy states until effectively settling at its lowest possible energy position while still in the conduction band until it meets the location of the hole, at which point electron hole pair recombination will occur and the electron hole pair will have been terminated. Okay, so that process of the electron hole pair recombining is what's called recombination, hence the name. As the temperature increases, the probability of covalent bonds breaking increases, which will yield more electrons and holes available for conduction. The rate at which recombination occurs is dependent on the number of electron hole pairs that are generated, which in turn also depends on the temperature. At thermal equilibrium, the rate of electron hole pair generation and electron hole pair recombination are equal so that the free electron concentration N is equal to the free hole concentration P, which gives us N, the electron concentration is equal to P, the hole concentration is equal to Ni, which is the intrinsic carrier concentration. Okay. So let's write those things down real quick. Electron concentration measured in per cubic centimeters. Hole concentration measured in per cubic centimeters. And this is intrinsic carrier concentration measured in cubic centimeters. Another way that we can express this is the whole, electron concentration times the hole concentration has to equal the intrinsic carrier concentration squared. This is what's known as the mass action law. And it effectively tells us what our concentrations will be when we start doping things, which is what we're going to talk about in a moment. Okay. Scroll back down because that went slightly too far. The intrinsic carrier concentration Ni is given by B capital T, so this is temperature to the 3/2 power multiplied by exponential function exp of negative Eg, our band gap, divided by twice kBt, where Kb is Boltzmann's constant, and it is 1.38065 times 10 to the minus 23 joules per Kelvin, or 8.61733 times 10 to the minus 5 electron volts per Kelvin. So I want to be clear here because there are going to be times where we will deal with Boltzmann's constant and spring constants in the same damn problem. K capital B will always be Boltzmann's constant. K and then some other subscript is overwhelmingly going to be a spring constant. Okay, so KB, I have designated that very specifically to be Boltzmann's constant. Neil. Depends on the situation that you're dealing with. If you're dealing with energies in electron volts, use the second one. If you're dealing with energies in joules, use the first one. They're the same thing. Since actually, let me talk about this very, very briefly here, because this is something that I see a lot of students, both undergrads and graduates, make a mistake on, and that is what the unit of an electron volt is. Okay, so 1 electron volt is defined to be the charge of an electron. So Q, the charge of an electron, and I'll give you a number for that in a minute, multiplied by 1 volt. Okay, that is what an electron volt is. Q here is 1.602 times 10 to the negative 19 coulombs. Since a volt is a joule per coulomb, 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. So they are the same thing, effectively. I'm just converting between joules and electron volts by using that conversion factor of 1.602 times 10 to the negative 19. Now, the reason why I'm bringing this up is because there are going to be a whole hell of a lot of times where we are going to see something written as KBT over Q, okay? Boltzmann's constant multiplied by temperature divided by charge, okay? KB over Q is just voltage. And then we scale it by temperature, okay? So KBT over Q is going to wind up being something close to 26 millivolts is what we're going to use. This is what we're going to call our thermal voltage later on. I see a lot of students try to calculate this and they get some weird asinine number, and it's because they don't understand what the unit of electron volts means. So if we have electron volts divided by the charge of an electron, that's just giving us a volt. And then we have some voltage that's very small, like 8.61733 volts, or times 10 to the minus 5 volts, and then we multiply it by a room temperature of 300 Kelvin, and we wind up getting about 26 millivolts, 25.9 and some change. So I would argue, don't do the calculation yourself with the units. It gets weird quickly. Just say it's a voltage that's scaled by some amount and you'll do it for that. So anyway, that's an aside there. I'm happy to go into it in more detail, but we have 17 minutes left of class and I have like 9 more pages of notes to go through. So it looks like we're going to keep on reviewing stuff on Friday. All right. So we have talked about how a intrinsic semiconductor behaves, meaning we have not introduced any impurities or anything like that. We've determined, oh, actually, sorry, let me go back here real quick. That went too far anyway. So this relationship for the intrinsic carrier concentration is obviously telling us the number of electron hole pairs that are generated in an intrinsic semiconductor material. This quantity B is what one textbook that I've used refers to as a material dependent parameter. This is just a lazy thing. In truth, B is related to the effective density of states in the conduction band and valence band, which is in turn has stuff to, deals with the effective mass of holes and electrons in the semiconductor. They're just lumping together a crap ton of complex, weird math into a single parameter that depends on a material. So I'm neglecting, I'm saying all this to say I'm neglecting a ton of physics by giving you this particular expression, because all of that background physics regarding effective density of states, effective mass, and all that kind of stuff doesn't really matter to the applications that we are using this stuff for, okay? So if I ever make you calculate an intrinsic carrier concentration, I'm going to give you B, and it's going to have really weird units that is all of that physics bundled together in a nice, neat little package for you to apply, instead of making you look up 10 things in tables to get the exact same number. Okay, so anyway. All right, now let's talk about extrinsic. Or doped semiconductors, okay? So, excuse me. At normal operating temperatures, most semiconductor materials do not have enough free charge carriers to be considered good electrical conductors, okay? So mathematically, our electrical conductivity is given by Q, the charge of an electron, times our hole concentration times the mobility of holes. Let's do mu P. Trying to decide whether I wanted to use mu P or mu H. I'm going to go with P. And then N, our electron concentration, times mu N. Okay. So not performing the calculation for you or anything like that. Just want to show you something here. For silicon's material properties at 300 degrees Kelvin, we would have about 3.022 times 10 to the minus 6 per ohm per centimeter of conductivity. So this is for intrinsic silicon at 300K. For copper at the same temperature, this is going to be about 5.952 times 10 to the positive 5 per ohm per centimeter. Okay, so copper is what we would consider a good conductor, really a very good conductor. And we can see that silicon's electrical conductivity at the same temperature without anything to help its conductivity out is 10 to the 11, or excuse me, 10 to the 11 times smaller, right? So ideally, effectively it behaves as an insulator. Ideally, if we want it to behave like a semiconductor, we want to raise that conductivity to somewhere around 10 to the 0, right? Or better. Just to be clear here, mu P here is the hole mobility, because we'll be dealing with this later on, measured in centimeters squared per volt second. Mu N is the electron mobility, measured in centimeters squared per volt second as well. All right, so in order to make the material more conductive, excuse me, impurities or dopants are introduced. So group 3 elements like boron and gallium which we'll consider acceptor dopants, only have 3 valence electrons. When added to a semiconductor, they, right, stylus, create, really more so donate, excess holes beyond the intrinsic carrier concentration resulting in a p-type material. So the reason why this works the way it does would be understood by looking at an energy band diagram. Okay. So we're going to draw another one of these things. And sorry, my allergies are bothering me again. Here's our valence band. Here is our conduction band down here. And then when we put the impurities in, what we are going to do is we are going to effectively introduce a new energy level that is somewhere inside that empty band gap, right? So acceptor atoms typically have ionization. Let's talk about it. All right, so I'm going to put, before I get too far ahead of myself. So this EA right here is going to represent the energy level of acceptor atoms. Okay. So it is pretty close to the valence band. This difference here is somewhere in the ballpark of 0.05 electron volts. Okay, so at temperature at 0 degrees Kelvin, this is still going to act like an insulator material because there are no free electrons, right? But as we increase the temperature, what we are going to see is that holes in the valence band can more easily jump up into that empty energy state, or sorry, electrons in the valence band, sorry, I misspoke. Electrons in the valence band can more easily move up into those acceptor points where they only had 3 valence electrons, right? So that's a state in the crystal, a physical place in the crystal where it's really looking for another electron to complete that covalent bond. Since it only takes 0.05 electron volts of energy to jump from the valence band up into the acceptor band, it's very trivial for electrons to move from the valence band into that acceptor band, leaving behind a bunch of empty states or holes in the valence band for conduction. This all happens on top of our intrinsic generation of electron hole pairs as well. Okay. So these acceptor atoms ionize very easily, and it happens at a pretty low temperature, so that by the time we're operating at room temperatures, we get hole concentrations on the order of 10 to the 15 to 10 to the 17 charge carriers per cubic centimeter. So we get a much more electrically conductive material, right? So another thing here, if Na, which is the number of acceptor atoms per cubic centimeter that we've doped our crystal with, is much greater than the intrinsic carrier concentration, then our hole concentration in our p-type material will be approximately equal to the number of donor atoms, or excuse me, the number of acceptor atoms, and our electron concentration in our p-type material will be essentially the intrinsic carrier concentration squared divided by the acceptor concentration, so that our mass action law is maintained. Holes times hole concentration times electron concentration equals the intrinsic carrier concentration squared. And it works out that way because that excess of holes in this case will allow thermally generated electrons to recombine more easily, so that we get a balance at thermal equilibrium. All right, so this is where we're going to stop for today. Now we're going to talk about what happens if we do group 5 elements, right? So group 5 elements, like phosphorus and arsenic, are called donor dopants, and they have 5 electrons. Excuse me, let me write this out. 5 valence electrons is a better way to do it. Okay. All right. When they are added to an intrinsic semiconductor, they create excess electrons in the conduction band beyond the intrinsic carrier concentration, yielding an N-type material. Okay. So very similarly, we can explain this, sorry, scroll back, looking at an electron band or energy band diagram, excuse me. So here is our valence band. Up here is our conduction band. The impurities are going to form a donor energy level, ED, that will be somewhere in the energy band gap. ED is very close to EC. Once again, somewhere in the ballpark of 1/20th of an electron volt. And what we're going to see is that since these donor dopant atoms have 5 electrons in their valence band, that 5th electron can easily be excited up into the conduction band. And once again, this happens alongside the thermal generation of electron hole pairs. And so in these N-type materials, we wind up having an abundance of electrons that are available for conduction. if Nd, the number of dopant atoms, donor dopant atoms is much greater than Ni, then the electron concentration for the N-type crystal is approximately Nd, and the hole concentration for the N-type crystal is approximately Ni squared over Nd. The last thing that I want to put here, and I'll just tuck it in right here. Typical doping concentrations for silicon range from 10 to the 15 per cubic centimeter to 10 to the 18 dopant atoms per cubic centimeter, okay? This seems like a whole hell of a lot of dopants, right? We're talking 10 to the 15 to 10 to the 18 atoms per cubic centimeter. How many silicon atoms are in a cubic centimeter of silicon? Anybody know? 5 times 10 to the 22, excuse me. So what that means is that even if we put 10 to the 18 dopant atoms, we're still doping in a parts per million regime, okay? So it's not enough, even if we're putting in that many, it is not enough to really change the mechanical properties of silicon. It still largely behaves like bulk silicon, but electrically it is much more conductive because all of those added free charge carriers due to the presence of the dopant atoms, okay? So even if we make this thing, if we put 10 to the 18 atoms per cubic centimeter, 1 out of every million silicon atoms has been replaced with an impurity. It still behaves like silicon for the most part, except for electrical. All right, so that is enough out of me for today.